Welcome back. In this lecture we're going to tie what we've been learning about these filter banks, which we first discovered as we investigated the properties of the Haar scaling and wavelet spaces. And then we generalized a bit into what we needed for perfect reconstruction under the assumption that we could choose our filters H and G independently of the Haar wavelet. Now we're going to tie those back into orthogonal basis functions and wavelets. So, as you recall, we had a structure that looks like the one shown here. Copy, and we put it on almost every slide. It's not copying. Copy. Paste. There we go. And I'll put it back up here for reference. So we found properties of these filters that could guarantee perfect reconstruction with a delay. And we decided that perfect reconstruction with a delay was acceptable, and so that was just fine. And that requirement was this. All other requirements were met because once we had our G's, we could come up with the H's that would give us the other properties. So, let's suppose that G naught is given. Then we can choose G1 of Z to be equal to negative C to the minus M, G naught, negative Z, negative 1. So here we are alternating signs on the samples. That's the negative Z. We're flipping our filter around from left to right. That's the negative 1 in the power of Z. And we are delaying. That's the Z to the minus M out there. Okay, so if we do this, then we get G naught of Z, negative Z to the negative M out front there, and this is going to be G naught Z to the minus 1 minus, and here we're going to have negative Z to the minus M, so that becomes positive. We have G naught minus Z to the minus 1, and G naught with minus C, we want that to be equal to the Z minus M. Okay, well, I know what you're hoping, and it's kind of what I was hoping too, but it didn't happen. We were hoping that this would give us the answer we all sought, but it just introduces a problem written in another way. So we define P of Z to be G naught of Z, G naught of Z minus 1, so the flipped version. And then we have the requirement that P of Z plus P of minus Z has to equal 2. I'm sure it's hard enough to keep track of everything that we're doing here. It certainly was for me the first couple times I saw it. And can you imagine coming up with this on your own? Makes you quite impressed with the people that did this, but it didn't happen overnight. And it didn't happen over the course of a single lecture or two. So we happen to know, just from the definition of P of Z, that it's going to have to be the Z transformers from P of N. And we also know from our definition up above that this is going to be the product of the transforms of our G naught. And if you remember your basic DSB from 3rd grade, you might recognize this whole G of Z times G of Z inverse as a special function, and we'll get to that in just a moment. So this could be the double sum over K and M of G naught of K and G naught of M Z to the M minus K. Now we're going to do one of our tricks. Remember, there are two basic tricks that solve most problems. One is that a change of order, moving things in and out of summations and swapping the order, and the other is swapping variables. So now we're up to the swapping the variables trick, and that gives us a sum over all n. So we've swapped the order and we've swapped the variables here. Wow, we're pulling out all the stops to prove this. G naught K minus N Z to minus N. Okay, so what is this? This right here I'll put parentheses around it, is just the autocorrelation function of G naught of N. So that's what I was, this is our special function. So this is and that is also equal to RP. So we now have a way to choose P of Z. Basically, we choose G naught of N so that its autocorrelation function is 0 everywhere except at n equals 0. And then we use our previous relationships to get our other filters. Okay, so that's not too bad. There are a lot of functions that we could come up like that. Radar specializes, people working in radar specialize in functions like that, but theirs generally aren't suited for the type of analysis that we want to do. So let's tie this to wavelets. And let's spell it right. Okay, so how does this relate to wavelets? Remember, let's put these relationships back up here. The S j minus 1 and is equal to the sum over k xk h naught 2n minus k, and we had wj minus 1 of n is equal to the sum over k of xk. So our scaling functions, our wavelet functions, are shown here. Remember, we're going from a fine scale to a coarser scale. Like so. So if we define a function u of n and just say, actually this is a vector. Think of it more like a vector. And then come back to this j minus 1 if n is just equal to the projection of un onto x and w j minus 1 of n is just equal to the projection of Vn with x. So the combination, we know this already, is that Un union with Vn form an orthonormal basis. So basically our discussion began with the Haar functions for wavelets, and it turns out that we can use other functions that would also give us a multi-scale approximation, and that's a key factor of wavelets. I'll just put it over here. Wavelets give a multi-scale approximation to a function. And we define that function as a function in continuous space, and we had wavelets in continuous space. And we defined in terms of the Haar wavelet that we had some relationship between a scaling function and a wavelet function that would enable us to break up these spaces to make them have the properties that each scaling space was orthogonal to a wavelet space that, when combined with a wavelet space, made up the scaling space at another scale. So we've already gone through that definition, and that worked, and then we showed for Haar wavelets how you could break this down into, once you had your finest resolution that you cared to have, you could get the coarser representations, which were the interior spaces in our Venn diagram. Instead of actually performing the projections, we could just perform operations on the scaling coefficients, and so that was great. So now we went from operating on continuous signals to doing only an initial operation to get our initial scaling function or scaling coefficients, and everything else looks like DSP. Then we used our DSP analysis to show that, hey, we could do these same types of operations and we could perfectly get our signal back as long as we obeyed some properties. And we found that this could come down to, it boiled down to choosing a function g that just had the property that its autocorrelation function is 0. Okay, so now we're trying to loop back around and tie that into the wavelets. So it turns out there are several properties that our scaling functions must have in order to be considered to be associated with wavelets. So let's put this here. We can use other functions than the Haar, other than the Haar basis. Or scaling function, but it has to have these properties. Okay, so the first thing that we want is an ortho basis. We've already become addicted to how much easier that makes life, and so we want v naught t minus k. Now here we're dealing with continuous functions again, so we're jumping back and forth with operating on the discrete coefficient to, right now we're talking about the actual continuous time signal itself. So we want this to be 1 for k equals n and 0, otherwise And so the first property that must hold is that we must have this orthobasis, and we're going to define for that V naught is equal to the span of this set of bases and actually, as we discussed before, this will have to be the closure of the span. We're just going to call it the span in the case of the basis, but we're going to denote the closure of the span with that bar over the top. Okay, so now we'll define Vj to be the closure of the span of Vj comma n of t for n being integer, and as you recall, we defined Vj comma n to be 2 to the j over 2 V naught 2j t minus n. Okay, so when we do this, we will still get that Vj comma n are orthonormal bases, and that's over our standard inner product, and that's easy enough to show, and we looked at that already for the Haar case. But now we're ready for property number 2. So far with property number 1, we said we have some basis that spans some space V naught, and it is an orthonormal basis. So next, we want that Vj has to be a subset of Vj plus 1, which means that if x is in Vj, there's an element of Vj, then x of t is of course an element of Vj plus 1. Okay, so that's the multi-scale approximation that we're concerned with. Now, lastly, we want P3. We would really like all of these approximation spaces taken together. In other words, limit as j goes to infinity of Vj, we want that to be L2 of R. In other words, we now have a basis for all x in L2 of R. So, there's nothing here specifically about the Haar Wavelet basis, and in fact we can choose other bases that will work, And this is related back to our function in this way, that G naught of n is equal to in other words, our function G naught relates our scaling function to the scaling function at the next level. So once we've defined that scaling function, and then its relation to its own self-scaled version will give us the filter G naught. So if it has, if our scaling function has finite support, a finite extent, then G naught will be a filter of finite length. And how do we actually choose G naught? Well, let me add, once we have G naught, this is going to tell us how we can build up our scaling function from our base scaling function. And the answers are not quite simple. There are more properties actually discussed within the notes, and we're not going to go into them, but they're there for you to note. And one of the things that we do discuss in the homeworks, at least some semesters, is the fact that if you choose your scaling functions and therefore the wavelets in a careful manner, you can have some really interesting and nice properties, especially for signal compression. One of them is vanishing moments, and this is discussed in the notes. Vanishing moments say that any smooth or any polynomial up to a certain order, when projected onto the wavelet, gives you a result of 0. So if you are compressing anything that has polynomial sections in it, then the wavelet coefficients will all be 0. It's very easy to compress 0. So that's a great idea. Compact support is really nice. Compact support means that the wavelet function itself only extends a certain distance. This is in contrast to Fourier bases that have infinite support. The Fourier bases continue on for all time, so having the wavelets have wonderful, nice properties, and they're localized. So when you do the wavelet analysis of a signal, the wavelet coefficients won't be affected by parts of the signal that are far away from it, nor will they ring out forever, which is another nice property. So go ahead and take a look at the notes for other details, but those are some of the neat properties. It turns out that we're not actually going to discuss coming up with wavelets. There tend to be entire graduate courses on wavelet theory where you don't even spend much time on figuring out how to come up with wavelet basis functions. But at least now we know kind of what some of the constraints are, where they come from, and why they are so useful in signal processing, namely compression, looking at signals at different scales, and so on. There's one other thing I want to bring up, though, before I end this, and that is that when we, let's do it this way. Oops. There. When we analyze a signal with a wavelet filter bank, if in general we look at, say, frequency on this y-axis here, time on this axis, and H naught is a low pass filter, as it generally is, and H1 is a high pass filter. And we plot kind of the energy of our coefficients and the impact on the frequency domain. What we find is that our scaling function, and let me pop back to here to illustrate what I'm talking about. The scaling coefficients here on the upper right, S naught, and then the wavelet coefficients, because of the high pass and low pass nature of it, we will have the we perform a low pass filter with H naught. You know what? I'm just going to copy this over to a new set of slides so we can discuss this in a little bit more detail. So what we have here is a low pass filter, a high pass filter, and then we downsample, and once again we do a low pass filter and a high pass filter. So what does the spectrum look like at each point? So we're going to do a low pass filter and then a high pass filter for the H1s. The high pass filter then, the output is in our wavelet coefficients. We're filtering these coefficients here. The low pass signal though shows up right here and downsampled. So what happens when it's downsampled? Well, we take our original low pass, and now it goes all the way out like so and aliases back on itself. But we don't care about the aliasing because we take care of that later. Remember, when we do the reconstruction, it cancels the aliasing, so we're okay. Now we have a full spectrum signal at this point right here. We do a low pass filter again and a high pass filter. So when we are finally done, out here at the right, that represents a tiny low pass fraction of our original spectrum. And the wavelet coefficients represent what is essentially the high pass part of a low pass signal, or in other words a band pass signal, except for this very first one, which is high pass. So now if we come back to this drawing, you can see that our spectrum is broken down like this. We will have a very low pass signal represented by our S naught. And since we've done so many downsampling operations, each coefficient now spans a large amount of time. It's basically the extent of the original filter times 2 to the number of downsamples gives the amount of time that represents. The corresponding wavelet coefficients look like that. Okay, but at the previous level, the extent is half as long, but the bandwidth is twice as much. Now we don't have any more scaling, so from this point out it becomes more and more like this. So pretty soon the the very first wavelet coefficients represent the high frequencies of the signal, and they have a very short temporal resolution. So we call this the time frequency tiling. And when you look at a Fourier representation, the time frequency tiling is made up of squares or rectangles of all the same size. But with wavelets, they differ in size according to the frequency. And one beautiful thing about this is actually closely related to what the ear does. Our ears are very good at frequency resolution at low frequencies, but not very good with time resolution at low frequencies. But we're very good at time resolution at high frequencies and not very good at frequency resolution. Hence, the piano scale doubles in frequency every time you go up an octave. It's not a linear scale, it's exponential. So this is the time frequency tiling of the wavelet transform.